All right, so now we're going to carry on with chapter five. So far, we finished section 5.1, where we introduced logarithm and exponential functions. So now we're going to switch our attention a little bit to the integration of these functions. And so we'll start out by integrating the natural logarithmic function. And it turns out that dealing with or taking derivatives of and integrals of the natural log is very straightforward, as is the case with e to the x. Okay, so um, we'll start by integrating the natural log of x, or at least not integrating the log of x. We're going to integrate 1 over x dx to give us back the log of absolute value of x. Okay, so if you look carefully here, you'll notice there's an absolute value sign here. If X itself is, for whatever reason, is guaranteed to be positive, you can drop the absolute value signs, but in some cases we can't be sure, so you will need them. So if you're doing an assignment, for example, with WebAssign, and it asks you for a logarithmic integral of some kind, don't forget about those absolute value signs because you might get it marked wrong without realizing what the problem is. But if you ended up with, like, in the second case, you've got u, if u is a function like x squared, which can't be negative, in that case, you don't really need the absolute value signs, but it doesn't do any harm to put it in there. So, if there's any doubt in your mind, just leave it there. All right. So again, these are the two rules that we need to know now. If we have 1 over x dx, we integrate that into log natural absolute value of x plus c. On the other hand, if u is which we know is a function of x, is integrated here, what do we end up with? Then we have the natural log of absolute u plus c. Okay, great. What about this one? Okay, so you've got the integral of 2 over x dx. And of course, that 2 there, obviously the first rule is very similar to this one. We just move the 2 outside the integral sign. And we end up with this case up here. So all we have now is 2 natural log absolute value of x plus c, and we're done. Great. Okay. Um, oh, I see what they did. For a second there, I wasn't sure where they got that x squared from. No, what they're doing is they're reminding us that if you have log x to the n, it becomes n log x. So what happened here was we have 2. So 2 log absolute x is therefore log absolute x squared. But of course, x squared is strictly positive. So therefore, we can just simply rewrite this as not with the absolute sign, but just simply x squared plus c, of course. I think they only did that example just so you can see that if the log is taken of a function that cannot be negative, then you don't have to bother with the absolute value signs. All right. What about this one? Does this remind us of one of these? Maybe, but now let's think of it this way. Suppose that u is 4x minus 1. Then du dx would be 4, and du would be 4 dx. So in order to use this form here, we don't actually have du, but we can supply this 4, and we've done this before. What we have to do is this. I'm going to both multiply and divide by 1/4. By four, I mean. So in other words, 1/4. Clearly, that's the same as the first expression because all I did was, like I said, multiply and divide by 4. But then we have a much more convenient form, of course. We can think of this as du over u. And now suddenly we know what to do. Plus c because these are indefinite integrals. And of course, then we have to replace the u with the definition, which is 4x minus 1. And because the 4x minus 1 could be negative, we'll leave it with absolute value signs. Okay, let me just neaten that up a little bit. Beautiful. Okay, so that's that. Now, for some of these cases, well, there's going to be a little bit of trickery involved. For example, let's take a look at this one. Now, we've run into a case like this before. Here's the problem here is that we have a rational function. The problem is that the degree of the numerator and the denominator are the same. That's not good for what we need to do. So one thing we can try to do to maybe break this up into a couple of simpler pieces is use long division and see what happens. Now we've done this before. Let's try it one more time. So let's see. How does that work? Well, I need something in the top, which when multiplied by x squared plus 1, lets me eliminate that x squared over here. So I'm going to go with, how about 1? I can't multiply by x because that would make the degree too high. So I'll put a 1 here. Now there's no 0 in that expression. So, I mean, there's no x, so I'll write it as 0x. Now remember, I'm subtracting the whole thing. So this becomes negative. These drop out. This becomes negative, but it has no effect. Stays at x, and this is negative now. So these drop out. And I can't go any further. This is my remainder. So what did we just prove here? So you're probably thinking, well, what's the big deal? Well, the big deal is that this integral is going to be very difficult. Instead, I can do this. I've got two simpler terms, each of which will be easier to integrate than the original function. Like for this one, I can let u equal x squared plus 1. Du dx is 2x. Du is 2x dx. So I need to supply that 2. So I'm going to do this. I'm going to both multiply and divide by 2. And now look what I have. The one on the left, I can just leave it as x. That's fine. So you can see where this is going. And of course, u is x squared plus 1. And that's guaranteed to be greater than 0. So I don't need the absolute value signs. And that's my answer. Okay. So the absolute value signs are optional in this case. And that's my answer. Okay. So the tricky part was recognizing that when you have something like this, um, the degrees are the same. That's going to be a mess. So division is at least a possibility. And you can see it did let us break up this original expression into two smaller pieces. And then each one of those individually was easier to take the integral of than the original function. And that's what are hoping for. Okay. What else do we have? Here they want you to let's see. So now here's a case where they're saying, well, listen, suppose we told you that dy dx equals 1 over x log x. Because there's a derivative, this is technically known or formally known as a differential equation. So I'm going to integrate both sides. First, I'm going to multiply both sides by dx. Then I'll integrate. And so y, or f of x, equals this integral. The only problem is we don't know what to do with it. So what they're recommending us, they're essentially telling us that we're going to use u substitution, but because we can't be sure what is the best choice, we could try u equals x. In the denominator, it could be u equals log x or x log x. So they're giving us a helpful hint to save us some time. They're telling us to try u equals log x. Then du dx is 1 over x. Okay. And du is dx over x. All right. How does that help? Okay, because this is du, and by having log x in the denominator, u is in the denominator. And so we know how that works. If we go back to the beginning, they told us, yeah, there it is. The integral of 1 over u du, or du over u, is natural log absolute u plus c. And here the u is log x. Now that looks very peculiar, but that's correct. The log of log x. Now, if they didn't give us that hint, we probably would have guessed wrong and made a mess, and then eventually realized that u should be log x. Sometimes with u substitution, you have to try multiple possibilities before you get to the right one. It's not always immediately obvious what to do about u. If you make a mistake, it's fine. Just try something else. Eventually, you'll get the right one. Man, have you ever seen that before? Log of x. That's very strange, but that's the correct answer. Aha, trig functions. Now we're going to integrate trig functions here, but in some cases we'll need to make substitutions because remember, we have that list here somewhere of basic trig formulas. I think they're on the next page anyway. Look here. Here we go. So what they're telling us is that we don't have, actually we do, don't we? What are they saying here? Oh, I see what they did. No. These are new formulas. They've decided to let us see these now. The ones that we started out with, the very basic ones, did not have one for the integral of tangent x. So what they want us to do is rewrite this based on the definition of the tangent. Um, Tangent x is actually the same thing as sine x over cosine x. So the integral, these two integrals are the same. Now we have to pick the u. So keep in mind, remember that the derivative of sine x is cosine x. So if we do this, so here's what we can do. We can replace this with, um, oh, that's not going to help, is it? Because the cosine is in the denominator. So I guess we better try something else. That might be better. But of course, then we need to supply negative. Let's try that. So what we'll have here is the new, right here we have our du, and here we have u. Well, there you go. This is exactly what we were hoping for. And that would be the final answer. All right. So the key to the whole thing there was using the correct u substitution. So by starting out with the sine, it didn't work out, did it? Not a problem. We just go ahead and try something else. So we ended up with u equals cosine x, and we ended up with the correct answer. Nice. So, um, so these are the functions. Um, what are we doing here? One square root, one plus tangent squared x dx. Wow. Now this one, um, what do we do now? All right. Well, here's what I want to remind you. We have these trig, sorry, Pythagorean identities. And the first one is always sine squared x plus cosine squared x equals 1. Now, if I were to, let's see. Now, there's actually two other equivalent ones that you can create from here. If I divide both sides by sine squared x, that gives me, now that's not the one that I want though. So what I can do instead is divide both sides by the cosine squared of x. And now this is now tangent squared x plus 1 equals secant squared x. Okay. So in other words, if you haven't memorized them, you can still derive them. Either divide the whole both sides by the cosine squared or the sine squared. That's where we get these other two from. You do have to memorize the first one, but I think this is one of those formulas that nobody ever forgets. It's like the Pythagorean theorem. Who forgets the Pythagorean theorem? Nobody. Okay. So anyway, what does that have to do with anything? Well, here's what I'm going to try to do here. Watch what happens. According to this identity, this is the square root of secant squared of x, which means it's secant x. And if you look at this list they gave us, what do you know? It's right there. So it's the log of secant u plus tangent u. In this case, u is x. And there we go. Oh, I almost forgot. We're evaluating this from 0 to pi, from pi over 4 to 0. So this is not an indefinite integral. It's a definite integral. So that means there's one more step. There you go. All right. So keep in mind, remember, this is called a definite integral. And what we're looking for is an actual number. So we're going to have, all right. So now the challenge is to find these on the calculator. The calculator doesn't have a secant button, but be aware that, so in other words, what you're going to do here is take 1 over the cosine of pi over 4. That's how you work around that. The calculator doesn't, you won't see a secant button on there. That's why, because they figure you knew this. Now, the other thing too is if you're going to use your calculator to figure this out, make sure it's in the radians mode. It's so easy to forget about that. So take a look. Um, mode, I've got it in radians. Okay, good. So the cosine of pi over 4 is, okay, now it says here 0.7071. I'm pretty sure that's the square root of 2. Let me just confirm that. Oh, no, sorry, it's radical 2 over 2. So that's the equivalent of being 2 over radical 2. But if you remember, we try never to have radicals in the denominator of any ratio. So we're going to rationalize it. By multiplying the entire expression by the ratio radical 2 over radical 2, which we certainly are allowed to do because that's the equivalent of 1. So this is equivalent to radical 2, but that's just the secant of pi over 4. We also need the tangent of pi over 4. All right, well, that's on the calculator at least. That helps. Oh, okay, I made a mistake. I made a typo somewhere. Um, oh, it doesn't like that. Oh, I know why. I made it. I typed a two instead of a four. All right. Much better. That's one. Good. Now, of course, I also need the secant of zero. Cosine of zero is one. Well, that's not very helpful. So the secant, we'll put it up here. Secant of zero is one. The tangent of zero is zero. Beautiful. All right. So we can make some substitutions into this expression up here. And we're going to have, uh, and again, don't forget, and we still at some point have to take natural logs. Secant pi over 4, we just found to be uh, radical 2. Then we add the tangent of pi over 4, which is 1. Secant of 0 is 1. Tangent of 0 is 0. Now, 1 plus radical 2 is a positive number, so I'll write it like this. Now, 1 minus 0, the log of 1 is just 0. So the final answer is the natural log of 1 plus radical 2. All right. Well, that was a bit involved. Yeah, well, they left it in as log 1, but log 1 is 0. So it says here that's approximately 0.881. Let me just confirm that. Yeah, 0.881. So if they ask you for a specific constant in, let's say, WebAssigned, let's say they ask for four places, which they often do, it would be 8814. Okay. Or they might just let you leave it as log plus 1 plus radical 2. All right, here we go. So this one looks like we might want to use U substitution. The thing that makes it possible is that because the degree of the numerator is less than the degree of the denominator. So let's try this. All right. Well, we do have the x. We don't have the -8. So let's do this. Okay. So I multiplied and divided by -8. And now I have du over u. And then I end up with, unless they rearranged it somehow, that'll be the right answer. So let's see which one that is. Negative 1/8, it looks good. Log negative 4x squared plus 9 plus c. So it's A. Yes. All right, what about this one? So again, it looks like it's a prime candidate for U substitution. Let's try this. Yeah, that's right. So do I have what I need? Yes, it looks like it because that means I just have u to the sixth, and these two give me my du. All right, that would be B. All right, nice. Okay, so that was kind of our look at integration of logarithms. So, what comes next? Now, the next section is completely different. And it's like they decided to have a little bit of a detour from our discussion about logarithms because what they're going to do here is show us or possibly remind us how to take the inverse of a function. Okay. So this could apply to any functions, although not all functions have an inverse. We may have to test for that in the first place. So they're going to start at the very beginning with this very basic idea. We've got these two sets, okay, and A is the set 1, 2, 3, 4. B is the set 4, 5, 6, 7. So we're going to illustrate what's called a relation as a set of ordered pairs. So yeah, okay, they're going to write like this 1, 4, 2, 5, 3, 6, and 4, 7. Okay, now, sometimes you see this type of setup illustrated with a slightly different set of graphs here. You've got over here, we have our X's, here's our Y's. Whoops. And we can show what X's are associated with what Y's. You notice how the first order pair is 1, 4. That means that X equals 1 is associated with Y equals 4. The second ordered pair is 2, 5, which means X equals 2 is associated with Y equals 5. And then similarly with the others, we have 3, 6, and 4, 7. All right, so what do we know from this? Each X Let's make this a little bigger. Even bigger than that. All right. Is associated with exactly one y. So this relation is also a function. Further, each y is associated with exactly one x. That this means that this function is one to one, which guarantees the existence of an inverse. And it's easy to determine what it is. What we're going to do is this. We're going to simply reverse the ordered pairs. And by the way, you may remember that the notation that we use for the inverse of a function looks like this. So here we have 4, 1, 5, 2, 6, 3, 7, 4. That's our inverse. Now, normally the inverse and the original function are written as an actual equation of some kind. Here it's just a set of ordered pairs. But the important thing is that we've reversed the roles of the x's and the y's. Okay. That's what it means to be an inverse. And oh, they're using that graph that I was okay. Um, the other thing that we want to notice is that we can prove that these are inverses, although we don't actually have a function here, but there's a way you can prove that they're inverses. Here's what has to be true. If both of those are true, well, that would prove that f and f inverse of x are inverses. If one of those is false, then they're not inverses. Or if both are false, they're not inverses. Okay, so here's a quick, simple example, which will hopefully illustrate this. It makes sense that x squared and the square root of x must be inverses of each other because if you do something like this, so in other words, the two are in offsetting each other. 3 becomes 9 with the original function. 9 goes back to 3 with the inverse. Okay. So that's how you know. Oh, and one more thing they're mentioning down here at the bottom. Um, the range and the domain are reversed with the function and its inverse. So in other words, the domain of f of x is the range of f inverse of x, and the range, let me just see if I'm okay. No, I want to follow along with the way they're putting it. All right, let's do it this way. I think that, yeah, that's more consistent. All right, that's fine. So in other words, the domain of f of x is the range of f inverse of x. The domain of f inverse of x is the range of f of x. Okay, now how do we find these inverses? Here they're giving us the inverse and they're asking us to prove that they're inverses. Um, so let's do this first. Then we'll see how to actually find the inverse. So we'll start with f of g of x. So that means all the x's become g of x. So clearly, the cube root of x plus 1 over 2 raised to the third power just gives us, they offset each other. And then we'll do the g of f of x. And now g is this cube root. The x has to be replaced with f of x. So we have the cube root of f of x plus 1 over 2. And now we replace that f of x with its definition, which was 2x cubed minus 1. And then we have, and we have x. And we're all set. So we just proved that they are, in fact, inverses. But how in the world did we know in the first place that they're inverses of each other? Oh, okay. So they're confirming it, but here's what they want you to see. Well, this is the graph that helps confirm it. And you can see they're mirror images of each other with respect to the line y equals x. So, in other words, the point xy here has to be matched by the point yx over here all along the two curves. Okay. Now, I'm not positive I drew in the right place, but you get the idea. Okay. It's not perfect, but for every xy on the one function, we have to have yx on the other function. And so this is the consequence. We can see from that line that they are mirror images of each other about the line y equals x. But that still doesn't answer the question. Um, I'll tell you what, let me show you how this works. I know they're going to have to get it to you eventually, um, but it's a surprisingly simple technique. And then, okay, so there's more information coming, but here's what you would do. Suppose you don't know what the inverse is. So you start by writing it with x and y instead of f of x. Now, if you notice, the xy's become yx's on the inverse. So what we're going to do is this. Reverse the two. And so that means that now suddenly we have x equals 2y cubed minus 1. And then the next step is solve for y. Whatever that is the inverse. So I divide both sides by 2. Now I take the cube root of both sides, and I have my result. And guess what? That's the same one they give us. Cube root of x plus 1 over 2. Yeah, there it is. That's that's how that really the most straightforward way of finding it. Now, you may remember from way, way back in your travels, um, there's a graphical test to determine if a relation is a function, and it's called the vertical line test. And how does that work? If I draw a vertical line, any vertical line, if it never crosses that function more than once, then this is a function. Actually, I should say the curve because we don't know yet that it's a function. It crosses the curve more than once. Then this is a function. Okay. So as you can tell just by looking at it, if you can draw any vertical line without crossing it more than once, then what you're seeing is the graph of a function. But it turns out there's another test we can do to see if a function is one to one, and it's called the horizontal line test. All right, so here's how this works. If a horizontal line never crosses a curve more than once, the function is one to one. And therefore has an inverse. That's why they're bringing this up now, by the way, not just for the fun of it, although it is fun, I guess, but because we need it. So let me show you a couple of cases here. So you can see already this one fails the horizontal line test. This one passes the horizontal line test. So what that means then is that y equals x squared does not have an inverse. Whereas over here, y equals x cubed does have an inverse. So it's a very helpful test to have to be able to just take a look at a graph and say, is it one to one or not? Well, here you go. Here's a quick and easy way to do it. That's important because if, let's say the question says, what is the inverse of y equals x squared? It helps to know that there isn't an inverse. The answer is it does not exist. Okay. You don't want to be tricked and start looking for an inverse that doesn't exist. So that's one way you can help yourself by looking at the graph and seeing if there is, in fact, an inverse in the first place. All right. So that's what this is for. Yeah, so they're using this example, x cubed plus x minus 1. It's pretty clear that this one passes the horizontal line test. But they're also telling us here that another way to test is if the function is monotonic, which means it is always increasing or always decreasing. Okay, that would be another way to tell if it has an inverse. Okay, if it is monotonic, which means it goes up forever or down forever, then it must pass the horizontal line test. It is therefore one to one, and it must have an inverse. This one, no. You can see just by looking at it, it does not pass the horizontal line test. Therefore, it is not one to one, and it does not have an inverse. Um, here's another one. F of x equals radical 2x minus 3. And you can see that they are mirror images of each other. And both of them pass the horizontal line test. Okay. Oh, and here's where they finally get around to showing you how to do it. Okay. So let's try this one just for the fun of it. Y equals radical 2x minus 3. So what you do is one, reverse the x's and y's. So this becomes x equals, and then 2 solve for y. So I square both sides, and then I add the 3, and then divide out the 2. All right. So, and then this is what they got to. This, yeah, and you could write it like this. And remember, the original function was 2x minus 3, radical 2x minus 3. All right. So what else should we do here? Oh, derivatives. So here they're just telling us that if f is continuous over its domain, so is its inverse. If f is increasing on its domain, then so is its inverse. If f is decreasing on its domain, so is the inverse. If f is differentiable on that interval containing c, and the tangent is not horizontal, then f inverse is also differentiable at that point. So here we go. Now here's a formula that could come in very handy. Now they're assuming that these are inverses of each other. So, um, here's one. F of x is 1/4 x cubed plus x minus 1. So they want us to find F inverse of 3. But they don't want us to solve for the inverse. So I guess what they want us to do is this instead. So they're telling us to, hmm, I think it would be easier to just find the inverse. You know what? Let's see what we can do. Of course, oh, you know what? Maybe what the problem is, it's going to be a really messy function. So what they'd rather us do here is just note that, okay. So they're using F inverse instead of G. That's why it looks like such a mess. All right, let's do that. Let's rewrite it slightly. Yeah, I can see why they don't want us to bother because it's going to be a nightmare. So you could rewrite this as, and then you can replace that with a 3. And so they're telling us that f of 2 is 3, which means okay. Okay. So they skipped that step. Okay. That was wrong of them. Oops, hold on a second. So that means that f inverse of 3 prime is 1 over um f prime of 2 because all of this has been replaced by 2. And since the original function was it 1/4 x cubed plus x minus 1 using the power rule. Okay, there's our derivative. And f prime of 2 would be, and that would be 4. Oh, sorry, 1 over, it's up here. It's 1 over. So therefore the final answer is not 4, but 1 over 4. All right, so that's that. All right, what else do they want us to do here? All right, well, oh my God, these are graphs. Huh. All right, I'll tell you what, why don't we do this? Let's do this one inverse, just to get some practice. Don't forget to turn it into y, or at least, I mean, I think it's easier that way. So, reverse the x's and y's, and then solve for y. Square both sides, and then we'll subtract, of course, that 4, and divide out the 5. And that should do it. Okay. So let's see, which one do they? Looks like it's C, and that's it. Okay. All right. So what was that? 5-3. 5-4. I guess we don't have time for 5-4 tonight, but 5-4 is, oh, okay. So now we're going to differentiate and integrate the exponential functions. We've already taken care of the logarithmic functions. Now we're going to do the same thing for exponential functions. Okay, so we're going to learn the rules. And by the way, they're going to come along and tell us, which we already knew, that the logarithmic function, natural log of x, and e to the x, the exponential function, are actually inverses of each other. And now we know how to prove it. And then we're going to learn how to take the derivative of exponential functions and the integral. And then all of a sudden we can start solving for some very complicated problems. Okay. So this is what we have to look forward to next time, and I'll see you then.